The last topic for this chapter is solubility and the KSP, or the solubility product constant. When we're dealing with equilibrium with solubility, we write the equilibrium expression as a solid dissociating. For example, if we have silver chloride, which is a solid, the equilibrium would be the solid as a reactant and the ions in solution as products. So when I write my KSP, or my equilibrium expression, KSP again stands for solubility product constant, it's going to look like this. It's the concentration of the silver ions times the concentration of the chloride ions. And for silver chloride, it turns out it's 1.6 times 10 to the negative 10. It turns out because we're dealing with solubility, these equilibrium constants are actually going to be really small. And the advantage of solubility and working with KSP is when I want to separate ions that are in a solution of multiple different kinds of ions, then if I can pick the right opposing ion, either positive or negative, to cause one thing to precipitate and not something else, then I can separate them. I need to know solubility rules, so brushing up on your solubility rules would be a good thing to do. So, just a brief reminder for solubility rules. Nitrates, compounds that contain nitrate are all soluble. Compounds that contain group 1 metals and ammonium ions and hydrogen ions are all soluble. Generally, solubilities are referred to in terms of the negative ions, and as I go down this chart, I tend to have fewer and fewer compounds with these negative ions that are soluble. So halogens are the compounds that we start seeing some insoluble. In general, it's lead ions +2, mercury +2, and silver. Then I have hydroxides and sulfides, sulfates, carbonate, phosphates, and a variety of others. These are the ones we're going to be working with primarily. And so refreshing your memory, remember solubility chart, I think, was part of Chapter 4's handout. So going back and refreshing your memory on solubility would be a good thing to do. How are we going to use this? We're going to use this in a qualitative analysis lab to give you an opportunity to try and figure out what ions are present in a solution. So let's see how this solubility stuff works. I can start first of all by trying to find the KSP, or the equilibrium constant, from something and that has a solubility of a certain concentration. Solubility means that when I dissolve the compound, I'm going to get a molar solution that has that concentration. So I have 1 times 10 to the negative 15th molar for bismuth sulfide. So in solution, my concentration when I get to equilibrium for bismuth sulfide is going to be 1.0 times 10 to the negative 15. Not very much is going to dissolve. So if that's my concentration of the compound, what is my concentration of bismuth ion? Well, I look at the formula and I say, okay, there's 2 bismuth ions for every 1 bismuth sulfide. So my concentration of bismuth ions is going to be twice my concentration of bismuth sulfide. So my concentration of bismuth ions at equilibrium is going to be 2.0 times 10 to the negative 15. My concentration of sulfide, again, there are 3 sulfides for every 1 bismuth sulfide. So if I have 1 times 10 to the negative 15 molar bismuth sulfide, I'm going to have 3 times that amount of sulfide. So my concentration at equilibrium of sulfide is 3.0 times 10 to the negative 15 molar. Now that I have solubilities, I can figure out what the value of the KSP is because I can just put these numbers in the equation. So I have KSP equals the concentration of bismuth ion, which is 2.0 times 10 to the negative 15. And I have to square that because I have that 2 there in the right side. And sulfide is 3.0 times 10 to the negative 15. And that gets cubed. So when I do the math, I find that KSP for bismuth sulfate is 1.1 times 10 to the negative 73. Not very soluble. Okay, let's go the other way. Here's a problem where I'm given the KSP value for copper 2 iodate. It's 1.4 times 10 to the negative 7. And I'm supposed to figure out its solubility. Again, when you're asked to find solubility, you're looking for the concentration of the compound. So of copper iodate, KSP allows me to find the concentration of copper ions and iodate ions. From there, I can figure out the solubility of the compound. KSP is given. I don't know what the concentration of copper ions is. I don't know what the concentration of iodate ions is, but I know their relative amount. When they dissolve, I'm going to get X moles of copper ion. I'm going to get 2X moles of iodate ions for every 1 copper iodate. So for KSP, I've got 1.4 times 10 to the negative 7. So my concentration of copper is just X. My concentration of iodate is 2X, but I have to square it. So I have 1.4 times 10 to the negative 7 This is 4x times x, so I get 4x cubed. So now I divide both sides by 4, and then if I divide both sides by 4, I get 3.5 times 10 to the negative 8 equals x cubed. Now I need to take the cube root of that and get x. And when I do, I find that x is 3.3 times 10 to the negative 3. It's a concentration, so it's a molarity. It's a concentration of what? Well, x was the number of moles, or the molarity rather, of copper ions. So that's the concentration of copper 2 ions. For copper iodate, I have 1 mole of copper for every 1 mole of copper iodate. So this is also going to be the solubility of my copper 2 iodate compound. So I can go from solubility to KSP, and I can go from KSP to solubility. Common ion effect. Well, when I put a compound, in the case of the example that's shown, calcium fluoride, I have calcium ions and fluoride ions that eventually go into solution. If I then add another compound, in this case they're showing that sodium fluoride is added, fluorine then becomes my common ion. When I have that happen, what that does is it decreases the solubility of my original compound. The other thing that I need to keep in mind when I'm dealing with common ions is the pH. Because some ions that I will be working with are affected by the hydrogen ion or the hydroxide ion concentration in the solution, I need to be aware of pH of my solution because that can affect the solubility. For example, barium carbonate is a relatively insoluble compound. It's relatively insoluble in water, but if I try and dissolve it in a slightly acidic solution, that increases its solubility. And the reason it increases in an acidic solution is now I have two equilibria going on. I have the barium carbonate equilibrium where I have barium ions and carbonate ions. And then I also have carbonate ions reacting with water. And so since that carbonate now is participating in two different equilibria, it's actually going to increase the solubility of the barium carbonate. Carbonates are being pulled into the second equilibrium with water, and so that is pulling more barium carbonate solid to dissolve. So common ion can either increase or can decrease the solubility of a compound. And we'll just modify that then, say, in most cases. So in most non-pH related cases. Let's take a look at this problem where we have calcium fluoride and then we're adding some sodium fluoride to it. All right, so we're looking for the solubility of calcium fluoride, and they're giving us a KSP in a 0.025 molar solution of sodium fluoride. So how do I start that? Let's take a look. Initially, my concentration of calcium is going to be 0. Because calcium fluoride doesn't dissolve. It's got a really small KSP. Sodium fluoride, on the other hand, is pretty soluble. It's got a group 1 metal ion, and so my fluoride concentration is going to be 0.025 molar. So when I set out my equilibrium, this is 0, this is 0.025. Now since calcium is at 0, then my equilibrium is going to shift to the right because I want to generate some calcium ions. So this is going to be plus x, and this is going to be plus 2x because I have a 2 coefficient for my fluoride ion. So I want to find out what that concentration is going to be, so now I'm going to use KSP and solve for x. So I have KSP equals the concentration of calcium ions times the concentration of fluoride ions squared. So I have 4.0 times 10 to the negative 11 equals x times 0.025 plus 2x squared. All right, when we've done equilibrium before, what have we done with values that are plus or minus x? Can we do it the same here? Our equilibrium value is negative 11. That's pretty small, so there's not going to be much calcium and therefore not much fluoride ion generated by calcium fluoride dissolving, so we can cancel this out. So now I just have 4 times 10 to the negative 11 equals x times 0.025 squared. X is going to be a really small number. We get x equals 6.4 times 10 to the negative 8. It's a molarity, so that's a concentration of my calcium ions. Since I have 1 calcium for every 1 calcium fluoride, it's also going to be the solubility of my calcium fluoride. And so there, I found the solubility of calcium fluoride when it's in a solution of 0.025 molar sodium fluoride. It's pretty small, not very soluble at all.